So in this video, I introduce how to compute arc length and surface area for certain functions. So before we go and discuss the arc length of functions graph and the surface area, if you rotate that graph around the x or y axis, we need to further limit ourselves to a certain class of functions called smooth functions. So a smooth function is just a function on an interval, so that on that interval, not only does the function have a derivative, but the derivative is continuous for every single value in that interval. In this interval, we're talking about a closed interval. The curve itself is called a smooth curve. Now, intuitively, a smooth curve then is a curve that doesn't have these things. First, it doesn't have a discontinuity in it, because otherwise, of course, the derivative wouldn't exist. It also doesn't have a sharp corner, because if it does have a sharp corner, then at that point, while the function is continuous, the derivative from the left and from the right of that particular corner, the derivative would be different values. The derivative would exist, it would just be different values. On the other hand, you also can't have what's called a cusp. A cusp is where there's a point where the function is continuous, but if you take the derivative and look the limit from the left and the right at that particular point, you'll notice that the derivative is not defined, it's infinite, but from one side it's positive infinity and from the other it's negative infinity. That way you have a vertical tangent line, but in this case they both come in to the same point like that, like a sharp needle-like point. And the last case is that you can't have a vertical tangent. A vertical tangent is just an occasion where you have the function is continuous at the point, and then from either one of the sides, the derivative, if you take the limit, is unbounded. Now, we need to limit ourselves to these particular functions because in order to use the formulas, we have to make an assumption about the derivative. And it's a little odd because all the pictures I've shown you, each and every case, the derivative is actually continuous. Because if you say a function is continuous, you only worry about those values that are in the domain of the function. At none of these places is the derivative defined at 0. And at every other place it is defined as actually continuous. So there's something even beyond this that we require. So you need to see at least one function that has a derivative, so it exists at a value, and yet the function in the end is not continuous at that value. So here's a good example of a function that has a derivative at every single x value, and yet that derivative is not continuous. In particular, it's not continuous at 0. That's surprising because if you look at the graph, it appears the slope at 0 should be 0 because the graph is kind of becoming more like a horizontal line, and around it the graph looks like a horizontal line. So you would expect that the derivative is continuous. As from the left and the right, it appears the slope looks like it's going to 0. And yet that's not true. This is a good example of a graph where you really shouldn't trust it, because we infer what we want from the picture, not from what is actually there. So let's go and investigate this function. First, it is certainly continuous everywhere, but the only place you'd have to worry is at 0. So let's go see why it's continuous first. So it's continuous because if you just go and take the normal limit as x approaches 0, that means x is not 0, I have to find the limit of that particular expression. But I remember that this particular inequality would actually be true. It's not hard to prove it. I'll leave that to you. All you have to do is remember that the sine of any angle is trapped between -1 and 1. I just put the absolute values in because it makes things easier later on. Now then, by the squeeze theorem then, since the limit of the absolute value of x squared, or its opposite, goes to 0 as x goes to 0, this limit, by the squeeze theorem, also goes to 0. But that's the value of f of 0. So this function is continuous at 0. It's therefore obviously continuous everywhere else, because everywhere else it's defined as x squared is sine of 1 over x, and that's continuous everywhere x is in 0. The next is what is the derivative then? What should the derivative be at 0? Because the derivative anywhere else is easy. We just do the derivative rule. So at 0, let's just apply the normal definition. There's the derivative rule as x approaches 0. But we know what f of 0 is. We know what x minus 0 is. We know what f of x is. And by simplifying everything, you get the same as this limit. Using essentially the same trick as before, you can show that this particular function, x times the sine of 1 over x, is trapped between two functions that are both going to 0. I'll leave that to you to figure it out. But then, at that point, since those two functions are going to 0, by the squeeze theorem, this limit is also 0. So that means the derivative exists at 0, and it's 0. But if this then is the derivative, I've done the derivative rule for the one on top, and I defined the derivative at 0 to be 0. Look at what happens, though, if you take the limit of the derivative as x approaches 0. The limit of the derivative as x approaches 0 would require me at some point to take the limit of the cosine of 1 over x as x approaches 0. That limit doesn't exist. So the limit of the derivative as x approaches 0 does not exist. So of course it does not equal the derivative at 0. Therefore this function is surprisingly defined at 0, and yet not continuous at 0. Now you may wonder why it looks like it is. It's because you have to look at the slope. Look at the line, the graph before the vertical line x equals 0. You'll notice the graph goes up and down and up and down. Ride that particular graph with a point and look at the tangent line. You'll notice the tangent line does this. It rotates and rotates, but as it goes, the wave that you see, it still goes up and down and up and down. It's just becoming more and more compact this way. It's happening. That wave going up and down is becoming faster and faster and faster. It takes less and less time to do this over and over again. Well, the tangent line then is going to become more and more steep as you go and oscillate back and forth. So it's almost like the derivative, the slope, is oscillating from -1, then to 2, then to -3, then to 4, then to -5, and so on. I just pick numbers at random. It's not actually those numbers. But you get the idea. It oscillates more and more away from anything. So of course, that limit would not exist. Now that you have a better understanding of what we mean by a smooth function and a smooth curve, let's look at their arc length. So assume that we have a function that is continuously differentiable on the closed interval from a to b. I've given you a sample graph right here. Notice the graph has no discontinuities, no corners, no cusps, and no vertical tangents. And then it doesn't have other weird behavior, as you would have seen in my last example. Go ahead and take the interval from a to b and subdivide it into n subintervals, going from x sub 0, x sub 1 up to x sub n, where x sub 0 is a and x sub n is b. At each of these x values, define the corresponding y value, and then that will then give you at least n plus 1 points on this curve. So for those points, I just want you to connect them. So connect consecutive points. That would then generate a polygonal line. The length of that polygonal line would then be about equal to the arc length. Okay, so now let's go ahead and focus in on the kth subinterval. That's from x sub k minus 1 to x sub k. Now, over that interval, there's a corresponding change in x and a change in y, and we'll use subscripts to denote that we're in the kth subinterval. I'd like to know then, what is the length of the line segment that we have here in red? Well, if you look at it, all we have formed is a right triangle, so we can use the Pythagorean theorem in order to find the length of that line segment. It's just the square root of the sum of squares of the two changes of x and y. Now, I will now use that the function is differentiable, because I can use the mean value theorem to say that for some x value in the kth subinterval, which I'll call c sub k, there has to be a value so that the change of y is equal to the derivative at that x value times the change of x. This is just a way to rewrite the mean value theorem. Just plug that into the length formula for that segment, replacing the change of y with an expression. Square everything out, take out common factors, and then simplify the square root of the square. Remember, the change of x in my picture here is positive, so I don't need an absolute value. That gives you another way to represent the length of the line segment, but in terms of the derivative at some point being squared. So the overall length of the curve should then be approximated by a sum of these pieces. If that's true, then I can take the limit of the norm of the corresponding partition of the summation of all these little pieces and declare that to be the arc length. This then, notice, is a limit of Riemann sums. But we also recall that the derivative wasn't just any function, it was continuous. So if the derivative is continuous, then that function also must be continuous on the exact same range of values from a to b. So I have a limit of Riemann sums of a continuous function. So therefore, I know that this limit exists and equals a certain definite integral. This is in fact why I insisted that the derivative was continuous. Otherwise, I had no idea why the limit of this Riemann sum even existed. So let's recap what I've done and also throw in a little bit more notation to help us out later on. If a function is continuously differentiable on a closed interval, so the derivative exists on the interval and that derivative is continuous on that interval, then the arc length of the curve from x equals a to equals b is equal to this particular integration from a to b of the square root of the quantity of 1 plus the derivative squared dx. Also, we like to use a notation ds that represents a very, very small length on that curve. So the curve is not straight, it's a curve. But as long as the change of x is incredibly small, for continuously differentiable functions, that curve is so much like a straight line that you can kind of pretend like it is. Because of that, we think that there's a connection between ds, dx, and dy. And in fact, if you just go ahead and draw the picture, you see that ds squared, that length, should be equal to dx squared plus dy squared. Now this is just a mnemonic. It's just a way for us to go and remember how these things relate to each other. They don't actually mean anything by themselves, but it's a way to go and help us remember how to generate formulas. So ds then is a length of a small portion of the curve. So if you integrate that, the integration of ds, you have to get arc length. That's just another way to write it. We also have that ds squared plus dx is equal to dx squared plus dy squared, and we use that later on in more difficult problems where we can't do the integral in terms of x, and instead we want to do the integral in terms of y, and we just want to remember how to generate the formula. Okay, so let's do a couple examples. I want to find the arc length of this function on the interval from 0 to 4. First thing I got to do is check out what is the derivative. So the derivative of this function would then be just x to the 1/2, and notice that that is continuous. That is continuous on the interval from 0 to 4. So the function f is continuously differentiable on the interval from 0 to 4. So I can go ahead and write down the formula for the arc length. The arc length will just be the integration from 0 to 4 of the square root of 1 plus the derivative, which is x to the 1/2. I just have to square it, dx. So that's the integral from 0 to 4 of the square root of 1 plus x dx. And we can rewrite that once to get 0 to 4 of 1 plus x to the 1/2 power dx. Continuing up here. That would then be, the antiderivative is just take the 1 plus x. We would then increase the power 3/2, and we'll just divide by that, or in this case multiply by the reciprocal of that power, and we'll evaluate it from 0 to 4. So if you plug in 4, you'll get 2/3 5 to the 3/2 power, and if you plug in 1, you'll get minus 2/3 of just 1 to the 3/2 power, which is 1. This is the answer. This is the arc length of that particular curve. Let's try one now that's a little bit more interesting. It's interesting because at the end we're going to have to do some clever algebra in order to rewrite our integrand. So I need, once again, I'll have to find my derivative. So the derivative would then be, in this case, e to the x minus e to the negative x all over 2. Notice that that is continuous on the interval from 0 to 2. Well, in this case, 0 to 1. So I'm allowed to find the arc length by the formula I gave you. So my arc length will then be the integration from 0 to 1 of the square root of 1 plus that derivative, e to the x minus e to the negative x all over 2 squared dx. No clever substitution is going to help us this time. We're going to have to just multiply that out. So distributing the product, that would give you from 0 to 1. You'd have a square root of a 1 plus. You'd have an e to the 2x. It's all over 4. And you'd have a minus a 2 plus an e to the negative 2x, and then dx. If you add that together, you'll get the square root of, using common denominators, the common denominator would be a 4. So you'd get e to the 2x. You'd wind up getting plus 2 plus e to the negative 2x all over 4 dx. Now that looks, I agree, that looks pretty bad. But one of the ways to go about finding arc length is having some kind of ability to algebraically manipulate the expression that's inside the square root to itself become a square. That way the square and the square root cancel. Clearly this will not work very often. In fact, that's why there's not many problems in your book where they say find the exact arc length. They just ask you to approximate it instead using your calculator. Here, though, we can rewrite it as the integral from 0 to 1 of a square root. You'd have e to the x plus e to the negative x all over 2. And that thing is being squared, dx. Now the square and the square root cancel, giving me the integral from 0 to 1 of a e to the x plus an e to the negative x all over 2 dx. And I do not need the square root, the absolute value on this expression, because when you take a square root of a square, you're supposed to put absolute value, but that expression is already automatically positive as the numerator is a sum of two positive numbers. To find that, that antiderivative would then be a e to the x, a negative e to the negative x all over 2, and I have to evaluate that from 0 to 1. So, just that was just continuing up here, and this will now continue up here. If I plug in 1, I get e minus an e to the negative 1 all over 2, and then I subtract what I get when I plug in 0. But if you just plug in 0, you get 0. So then our answer then is the arc length is e minus 1 over e all over 2. And if you want to simplify that complex fraction, you go right ahead. But that is the arc length. Let's do a more interesting problem and find the length of the curve of y equals this particular integral from x equals 0 to x equals 1. I provided for you a sketch of the graph here in the upper right hand corner. Just to verify, notice that when x is 0, y is 0. And if you replace x in the equation with 0, you're replacing the upper bound with 0. So you wind up doing an integration from 0 to 0, so of course y is 0. So that looks reasonable. I would like to know the arc length. To do so, let's just quickly check. Let's make sure the derivative is the continuous function. By the fundamental theorem of calculus, this derivative has got to be just x minus 1 times x minus 3, and I take that square root. And that is certainly continuous. That is continuous on that closed interval. So I can use the arc length formula. So I need to know then what's the integration of the square root of 1 plus the derivative squared, which it gets rid of the square root. So you have x minus 1 times x minus 3 dx as we do the integration from 0 to 1. Now there's no simple substitution that's going to save us this time, so I'll use the second technique I showed you. I'm going to just multiply it completely out and just hope that the inside is a perfect square. That way the square and the square root just cancel. So if you just go ahead and distribute through, this will give you from 0 to 1 of the square root of 1 plus, we'd have an x squared minus a 4x plus a 3 dx. And that, of course, leads to equals the integration from 0 to 1 of the square root of x squared minus a 4x plus a 4 dx. That then is the integration from 0 to 1 of a square root. The inside's really x plus 2, x minus 2, that quantity squared, dx. And now the square and the square root cancel, giving you not x minus 2. It has to give you this time the absolute value. Why? Good question. It's because otherwise x minus 2 would be negative. Because we're working with numbers from 0 to 1. So otherwise it'd be negative. So I have to use the absolute value this time. But I can get rid of it because I know I can make the inside positive. Right now it's negative. I'll make the inside positive by putting a negative out front. So now all I have to do, just continuing up here, I have to do the integral from 0 to 1 of 2 minus x dx. And that's easy enough. That's 2x minus 1/2 x squared, evaluated from 0 to 1. If you plug in 1, you get 2 minus 1/2. If you plug in 0, you get 0. So the answer is, that's just 3/2. And that's the answer. That's the length of that curve. So as our last example, let's find the length of the curve y equals x to 2/3 on the interval from 0 to 8. So as I've done before, check out the function's derivative. And notice the derivative would wind up being 2 over 3 times the cube root of x. And that is not continuous on the interval from 0 to 8. So I can't use my normal technique. So instead, I'll notice that the graph I'm looking at looks like this. And notice that if I pick a single point and then look at the direct line segment, that segment represents our ds. Notice that I can pick the y-coordinate, and if the y-coordinate were to increase, you see how the point would go from the lowest point down here to the highest point up here. More importantly, it would travel over the curve only once. So instead of partitioning the x-axis, I'll partition the y-axis so that the arc length should then be equal to the integration over the values of 0 for y up to the value of 4 for y, just by finding the corresponding y values for these x values. So the integration then is from 0 to 4 of the square root of 1 plus, you can think of it as the derivative of the x in terms of y instead, squared dy. Now, if you look at the formula here, if you just solve for x, you would get x equals y to the 3/2 power, and that's on the interval as y goes from y equals 0 to y equals 4. And that would then be the integration from 0 to 4 of the square root of 1 plus. Now I need to know then what is the derivative of this x, but in terms of y. That would then be a 3/2 y to the 1/2. And that is certainly continuous. That is continuous on the interval from 0 to 4. So I'll just take 1 plus that derivative, 3/2 y to the 1/2 squared dy. So the integral then is from 0 to 4 of the square root of 1 plus, you would have 9/4 y dy. And I'll leave the remaining integration to you, as it's very similar to the first problem I did, in fact, so I won't waste your time. Instead, you might wonder, where did I get this formula from? Like, how did I know that would be the answer? Well, remember that ds is the square root of x squared plus y squared. This is a mnemonic to help us remember how to get the answer. So that this is essentially what we did when we found the overall length of the segment. It was the square root of the change of x squared plus the change of y squared. I just did limits to get dx's instead and dy's. So think of this as take and factor out a dy squared. You will then have a dx squared over dy squared plus 1 plus the square root of dy squared. And you can rewrite that as the square root of 1 plus dx over dy squared dy. And that would be then the portion that you have to integrate in terms of y. It's basically the exact same formula that we got in x, but it's just in y. And we did the derivative in terms of y, not x. I think we've done enough examples with arc length, don't you? why don't we move on then to finding surface areas of our solids of revolution. Now, if you remember how we go about finding those things, is that we take a region and rotate it around an axis. What we'll do is worry about only a curve and rotate it around an axis. That will then give us a surface. I want to know that surface area. So the simplest curve we can work with is a line segment. Let's suppose we take a line segment that lies in the same plane as some axis. Pretend that the line segment does not intersect the axis. And then we'll rotate that line segment about the axis. Now, my length of my line segment will be L. In order to further define its position relative to the axis, I'll need the two distances that the ends of that segment are from the axis. So we'll call that capital R and little r. The actual numbers here don't matter. I just need some kind of number, some kind of symbol to represent those distances. When you rotate around, you get what's called a frustum. I want to find the lateral surface area of that frustum. So, in order to do so, what I want you to do is to take a plane that goes through the axis of rotation. It will intersect this lateral surface area twice. It will then essentially make two lines that are a lot like what you see in L. Just take one of them and cut it. When you do so, and lay the object flat, we get this region. I want to know the area of that thing. That will then give me the lateral surface area. Well, notice that the circumference around the top circle in my frustum and the circumference around the bottom of that frustum is actually the inner lengths and the outer length of the donut that you see in my particular flattened out surface area. So, also notice though that if you think of this as two circles, portions of circles, in this case what we call sectors, and take the difference of these two sectors, the one in blue, the one in white, that gives you then what's left over, the thing in red, that gives us our area that we're actually trying to compute. So I need, in order to find the area of two sectors, I need the radii for those sectors, and I need the angle for that sector, for the central angle. So then here are the radii. We'll call them L1 and L2, labeling them in common to the length of the circumference, or at least the outside arc, tangent arc, for your central angle. So L1 goes with S1, L2 goes with S2, and then we have a common central angle for both of these sectors. We'll call that theta. I need to, in the end, find the area in terms of L, little r, and capital R. So a lot of these symbols are going to go away when I'm done. But this, then, is the area of the portion in red, being the difference in the areas of the two sectors, whose radii are L1 and L2, and whose central angle is theta. Notice that you can factor to take out some common factors. You can then factor the corresponding difference of squares to get this. We also notice from the picture that L1 minus L2 is just L, so we can get rid of that right away. And then also at the same time, I chose to distribute the theta through the expression. But I remember from early trig that if you ever take the angle in radians and multiply it through the radius, you get the length of the subtended arc. So theta times L1, that's just S1. Theta times L2, that's just S2. But from the frustum, I noticed that, the frustum, notice that S1 is just the circumference of that circle whose radius is R. So I know what S1 is in terms of capital R, and I know what S2 is in terms of little r. It's just the circumference of those two circles. Just take the half and bring it in and factor out the 2 pi. By doing so, you get that formula. In other words, the lateral surface area is 2 pi times the average of those two radii times the length of that one segment. It should not surprise you then that we can now find the surface area of the surface generated by rotating a segment around the x-axis. It's much like I did with Arclength. It's just a slightly longer setup. So we could still do the same thing. We could take the interval from A to B and partition it to get x values. That would then generate points. That would then generate segments. I would then rotate each segment around the x-axis, creating multiple frustums. And then, after I've done that, I would then find the corresponding surface area of each lateral portion of that frustum. So, by doing so, and taking in the limit, you wind up getting this integral. So the surface area generated would then be the integration from A to B of 2 times pi times the function value times the square root of 1 plus the derivative squared dx. The only part here that might be confusing is why did I not take an average of values? Because it's an average of radii, right? Well, in the interval dx, you have 2 radii, big R, little r, but you're using an x value in between, and the average of these two things, these two lengths, should be basically the same number, because if there's almost no change in x, there's almost no change in the function values. So the average of these two things is basically the same as just take the function at x. That's why we don't have an average of two values. Instead, we just have f of x. Now, these integrals can become even more difficult than the one we had for arc length. But if you want to compute them and get the exact answer, we're pretty much forced to do the exact same tricks we did with arc length. So we either use a clever substitution, or we hope that the expression inside the square root is actually a square itself. So those two things cancel. Since they're basically the same techniques, I'll just go and do one problem as an example. Let's find the surface formed by revolving the curve y equals x cubed from 0 to 8 about the x-axis. So let's see, I'm going to draw a little picture to help us out a little bit. So you have the cubic graph. We're going from 0 to 8. And I'll go about this axis. I think of it as I pick the singular x value, I get my segment ds. I need the radius, which in this case is going to be just my function at x, if I've picked my certain x value. So the surface area will then be the integration from 0 to 8 of the 2 times pi times my radius times the square root of 1 plus the derivative squared dx. But I can only do this if the derivative is differentiably continuous. So the derivative here is 3x squared, and that certainly is continuous on the interval from 0 to 8. So we're fine. So this becomes then the integration from 0 to 8 of 2 times pi. The derivative, the function was x cubed. I then have the square root of 1 plus the derivative 3x squared, that thing squared, dx. So that is the integration from 0 to 8 of 2 times pi times x cubed times the square root of 1 plus 9x to the fourth dx. So why don't we go ahead and go through the process of u substitution this time. So u would then equal to 1 plus 9x to the fourth. So that du would then be 36x cubed dx. So 1/3, so 1 over 36 du would then be x cubed dx. And for certain x values, I get corresponding u values. When x is 0 or 8, u would then be, since u is 1 plus 9x to the fourth, when x is 0, u is 1. Oh no, and then when, it's going to be a big number, and then when I have x is 8, I would then have that u is 1 plus 9 times 8 to the fourth power, which would then be something truly huge. It will be 36,865. Good Lord. Okay, good. That's fine. So then the integral then becomes, you'd have the integral from 1 to 36,865. You have our 2 pi still there. Our x cubed dx becomes 1 over 36 du. And then the square root becomes the square root of u. That then becomes, I would have 2 pi all over 36. This is really u to the 1/2, so the antiderivative is I increase the power by 1. I multiply by the reciprocal of that power, and then I evaluate that from 1 to 36,865. So we get a not so nice answer. That would then be, so you have 4 pi over 36, that's pi over 9. Divide by 3, that's pi over 27. So you have pi over 27. Further multiplied by 3,686 36,865 to the 3/2 power minus 1. That's the answer. That would then be the area of that surface. So that gives you a basic introduction to arc length of smooth curves and the surface area when you take such a smooth curve and rotate it around the x-axis. Of course, there's also a formula for doing the same thing, but we're revolving it around the y-axis. You can probably guess what that formula looks like. Also, though, I very sneakily increased your understanding of differentiability and continuity because I gave you an example of a function that is differentiable everywhere, and yet the derivative, even though it exists, at that value, the derivative is actually not continuous.